algorithms. Let us start with a recap of what we have done till now. We are given a problem and we want to solve it algorithmically. In order to have an algorithm to solve a problem, we have to follow the following steps. Specify the problem with the precondition of the input and the postcondition of the output. Design an algorithm or design an algorithm idea. Construct the algorithm correctly and then analyze the running time. Then we saw that recursion is a powerful algorithm design technique. We use recursion as follows. We are given an instance of the problem, deconstruct the instance or the input into sub-instances. Each sub-instance is strictly smaller in size. Solve the sub-instances recursively. From the sub-solutions, we construct the solution to the given instance. These three steps form the recursion step of the algorithm. Every recursive algorithm should also have at least one base case. Then we saw how we can analyze the running time of recursive algorithms. The running time of recursive algorithm can be expressed by a recurrence relation. We can solve a recurrence relation using one of the methods. The simplest method is unfold. But unfolding a recurrence relation may not be useful for all recurrence relations. Then we saw recursion tree. When an instance is broken into two or more sub-instances, we can analyze the running time of the algorithm using a recursion tree. The recursion tree happens so often that we can sum up the result in master theorem. In the last class we discussed there are three possibilities. One is most of the work gets done at the root of the recursion tree by the call to the algorithm. Case 2, most of the work gets done at the leaves of the recursion tree by the base case calls. Case 3, every recursive call does an equal amount of work. Master theorem sums up what is the running time for each of the three cases. We did not discuss that. I have left the matter in the slides. Please go through it as your self-study. I may prepare a short video for master theorem. Substitution I do not discuss. Again, I leave it to you as homework. The material is there in the slide. In this class, we want to analyze the running time of iterative algorithms. Till now, we have analyzed the running time of recursive algorithms. We just pointed out the relationship between recursive algorithm and iterative algorithm. When the recursive algorithm is tail recursive, it is equivalent to an iterative algorithm. That's all we have seen. But you are so familiar with iterative algorithms that I think I can go straight away to present iterative algorithms and show you how we will analyze the running time. This is the outline for today's discussion. How we analyze iterative algorithm. What is the abstract machine that we use for analyzing iterative algorithms? And then we illustrate how we analyze the running time of iterative algorithms with a few examples. The last note is what is the order of growth. Till now we have not discussed. We will discuss it in tomorrow's class. Okay. No need to read all the content. I will just highlight the most important thing. What is analysis? Calculating mathematically. The word analytically means mathematically. The resources such as time, memory, disk space required for executing an algorithm. And I have highlighted without actually executing the algorithm. That is called analysis of the algorithm. How long the algorithm takes to run to completion. How much memory space is required to run to completion. How much disk space is required to run to completion. We want to compute the amount of these resources. How much time, how much memory, how much disk space. But actually, we don't want to execute the algorithm. So we compute the amount of resources, time, memory, disk space mathematically. The question is, what is analysis of algorithms? Even though I have mentioned three resources, time, memory, disk space, primarily we are interested only in the time. How much time the algorithm needs for execution to run to completion. We call that running time of the algorithm or time complexity. Similarly, how much memory is required by the algorithm to run to completion, we call space complexity. Both running time and space complexity are measures of performance or efficiency of the algorithm. Those two words are important. Space complexity and time complexity. By complexity, we mean efficiency or performance. Note this word. Complexity does not say, oh, how complex or complicated the algorithm is. Complexity is a technical word for efficiency or performance of the algorithm. When I said both running time and memory space are important, most of the time in an algorithms course or when we study algorithms, we are occupied only with analyzing the running time of the algorithm. What is the reason? Out of the two measures of complexity, we will be primarily interested in the running time of the algorithm for two reasons. Number one, running time is more important of the two resources, time and space, time and memory. And more importantly, between the two, running time is more tractable mathematically. Space requirement often is not more tractable. Why do we need to analyze the performance of algorithms? There are two reasons. One is we are actually interested whether the algorithm is efficient. In the last class or in the last two classes, we mentioned this. When do you say an algorithm is efficient? If the running time of the algorithm is polynomial or better, we say the algorithm is efficient. The running time is big O of n. Big O of n squared. Big O of n cubed. Big O of n power 2.7, something like that. These are examples for polynomial running time. In addition, n is also linear. Suppose it is n log n. N squared log n. This is also okay. If it is exponential or factorial, we say the algorithm is not efficient. So our primary interest lies in finding out efficient algorithms. Algorithms which run in polynomial time are better. We are also interested in comparison of the algorithms. Suppose we have two or more algorithms to solve the same problem. Which algorithm performs better between two algorithms, A1 and A2? A1 is more efficient than A2 or A2 is more efficient. A1 takes lesser time or A2 takes lesser time. These are the two purposes, intention behind analyzing the algorithms. What is efficient? Is the algorithm practical? And then comparison. To analyze the running time of the algorithm, first thing we need to do is to choose a machine. On which machine? What is the target machine on which the algorithm will be executed? We do not want to choose a real machine such as 80, x86 or 68,000 and so on. A real machine is very complicated. Its architecture, instruction set, speed. Our goal is to find out, one, is the algorithm efficient? Is it practical? Two, is the algorithm better or worse than another algorithm? For these two goals, we do not need a real machine as the target machine. We want to have a simplified abstract machine. For a simplified abstract machine will be sufficient for our intended goals. The actual machine, if we analyze the running time of an algorithm on an actual real machine, the analysis is too tedious. And the resulting running time has too many details which are unnecessary. All I want to know is just answer this question. Is the algorithm efficient? Is the algorithm practical? Yes or no? To answer this question, I don't need so many details as given by an actual machine. Or if my goal is to compare two algorithms, just tell me whether algorithm A1 is better or A2 is better. Again, I don't need the actual machine. It furnishes me too much details. The simplified machine or the abstract machine that we use for analyzing the running time of an algorithm is called random access machine, famously abbreviated RAM. Don't confuse that with random access memory. A RAM model defines a set of basic instructions or basic operations. And here, this is how we define a basic instruction in the box. The characteristic of a basic instruction is this. A basic instruction can be executed taking only constant amount of time. Very important. It does not depend upon the input size. Any instruction, any operation that can be done in constant amount of time, I call that a basic instruction or a basic operation. Example, all arithmetic instructions such as add, subtract, multiply, divide are basic instructions because regardless of the two numbers that we multiply, it takes the same amount of time. Whenever we have an algorithm, all that we have to do is identify what is the basic instruction or the basic operation performed by the algorithm. Then just count the total number of times the basic instruction is executed by the algorithm. Very simple. How do you analyze an algorithm? Count the total number of times the basic instructions are executed. There may be one or more basic instructions. Most often I just identify one basic instruction. But even if there are two basic instructions or three basic instructions, you just treat them all equal because every basic instruction takes a constant amount of time. And count the total number of times. That's it. This is key. Basic instructions take constant time independent of input size. Important. Examples, arithmetic such as add, subtract, multiply, divide. Comparison, less than or equal to, greater than or equal to, not equal to. Logical, and, or, not. Memory access is also considered a basic instruction. You have a register, you have memory, this is load, and this is store. Those two are constant. Okay, in a high level algorithmic notation, I use assignment. On the right side, you have an expression. On the left side, you have a variable. This would be considered a basic instruction, assignment operation. Okay. In contrast, loops and function calls take varying time. Two loops do not take the same amount of time. How long a loop takes to run to completion depends upon how many times the loop body is iterated. Therefore, a loop is not a basic instruction. Similarly, function call. Because every function call or subroutine call takes an input. How long the function call takes to finish execution depends upon the input size. So examples of not basic operations are loops and subroutine. We also assume one level of memory hierarchy. Instructions and data are in memory. So that's all about random access machine. Okay. Now for the very important idea. How do we calculate, analyze the running time? We measure running time of an algorithm in terms of the total number of basic instructions executed. We have abstracted away the architecture, instruction set, and the speed of computer. It doesn't matter. What is the speed of the computer? What is the instruction set? What is the architecture? This is the outline that we follow for analyzing the running time of an algorithm. Identify the basic instructions in the algorithm. It may be just one. Count the basic steps. How many times each basic instruction is executed? Running time is simply the total number of times the basic instructions are executed by the algorithm. That will depend upon the size of the input n. N is the input size or problem size or instance size, whatever. The running time is denoted by T of n, T for time, n for the input size. T of n is a function of the input size n. For the same problem size n, the running time also depends upon the properties of the input. If the array is ordered, we will get one running time. If the array is not ordered, we may get another running time. So T of n depends not only on the input size n, but also on the properties. But most of the time we will ignore the properties and analyze it only as a function of the input size. All right. So till now, this is what we have discussed. We want to calculate the memory space and running time required to execute the algorithm to completion without executing the algorithm itself, mathematically. We analyze the algorithms. We want to find out whether the algorithm is efficient, whether it is polynomial or better. Then for comparison of two algorithms. How to analyze an algorithm? Identify the basic instructions. Count how many times each basic instruction is executed. Total the count. That's the running time of the algorithm. Example. Algorithm is to sum an array A, item 1 to item n. Input is an array A, 1 to n of n numbers. Output S is the sum of the numbers, sum of the items of A, 1 to n. Initialize S to 0. This loop is iterated n times. After each iteration, S is equal to sum of 1 to I. After first iteration, it will be sum of 1 to 1. After second iteration, it will be S is equal to sum of 1 to 2. After third iteration, S is equal to sum of 1 to 3. After n iteration, S is equal to sum of 1 to n. That's very, very simple. To achieve that, all we have to do is execute this assignment. S becomes S plus A at I. This property is called loop invariant. What is a loop invariant? Loop invariant is a property between the variables of the loop. What are the variables? S is a variable, I is a variable, even A1 to n is a variable. But A1 to n does not vary. S keeps changing, I keeps changing. Every time we iterate the loop, both variables S and I change, but the property does not change. S changes, I changes, but the property that S is equal to sum of the subarray 1 to I does not change. Such property is called loop invariant. So loop invariant is a property that remains true, that holds good for each iteration at the start of each iteration of the algorithm. This implies the loop invariant is true just before we enter the loop and just after the loop has terminated. So just after we have terminated the loop, S is equal to sum 1 to I is true. Since I was n in the last iteration, After the loop has terminated, this is equal to sum 1 to n. All right. So, that's the argument about the correctness. But in this class, my primary focus is not on the correctness of the algorithm, but on analyzing the running time. How many times? Okay. This is the basic instruction assignment. S becomes S plus A at I. Let it take time C3, the constant time C3. How many times this assignment is executed? N times. What is analyzing the running time? Count the total number of times a basic instruction is executed. So the total number of times this assignment is executed is C3 times N. How many times this is executed? This assignment, just one time, maybe C1. It's a constant operation. And there is also a loop. This is this also results in a number of instructions. At least there is a comparison. Is I equal to N? Is I equal to N? Is I equal to, okay, is I equal to N plus 1? Is I equal to N plus 1? Is I equal to N plus 1? This comparison is done N plus 1 times. The first N times, the comparison is false. Oh, I is not yet N minus N plus 1. I is not yet N plus 1. I is not yet N plus 1. In the last comparison, I is equal to N plus 1 and therefore the loop terminates. Therefore, this comparison, one assignment and comparison. These two are the basic operations. This comparison is executed N plus 1 times. Assignment is executed N times. Comparison cost, the time taken is C2, time taken is C3. Therefore, what is the total amount of time taken? C1 plus C2 times N plus 1 plus C3 times N, as shown here. Gather the coefficients of N and the constants. This will be C2 plus C3 times N plus C1 plus C2. Replace C2 plus C3 by another constant A and C1 plus C2 by another constant B. Therefore, the running time of algorithm sum is AN plus B. Later on, we will say, ignore the lower order terms. Ignore the constant coefficient and just say T of N is equal to big O of N. This we call asymptotic running time. Running time in the limit. When N becomes very large, this A and B can be ignored. Yet another algorithm. Algorithm, linear search. We are given an array A 1 to N. 1, N, and a target T. We want to find out where T is found in the array 1 to N, A1 to N. And if it is found, return the index, the position of T. If it is not found, return an invalid index such as N plus 1 or 0. That is how I define array A1 to N of N numbers and a target T to search for. Output is I such that A at I target is not found in this part. A at 1 to I minus 1. Target is at I. This is one possibility, one case. If the target is in the array at all. If the target is not in the array, T is not found in array 1 to N and therefore we will return N plus 1 or something like that. I write the algorithm this way. This is the loop invariant. T is not in the subarray 1 to I minus 1. Okay. To start with, I becomes 1. Therefore, we say T is not in subarray 1 to 0. Subarray 1 to 0 is empty. So, T is not in 1 to 0. First time. After one iteration, T is not in 1 to 1. After that, T is not in 1 to 2. After that, T is not in 1 to 3 and so on. The one extreme case, T is not in 1 to N. The termination condition has two sub-conditions. Until I is equal to N plus 1. Okay. Suppose, so if I is equal to n plus 1, the loop will terminate. Other possibility, if a at I is equal to t, then also the loop will terminate. So the loop will terminate under one of the two conditions. Even if one condition is true, the loop will terminate. Okay. About loop invariant, I said the loop invariant is true at the start of every iteration. The loop invariant is true at the start of the loop. The loop invariant is true when the loop terminates. Therefore, here the loop invariant t is not in 1 to I minus 1 is true, and either I is equal to n plus 1 or a at I is equal to t. T is not in 1 to I minus 1 and I is equal to n plus 1. This is equivalent to t is not in 1 to n. Alright. What will be returned? We are returning I plus 1, which is simply n plus 1. Our convention is if it is n plus 1 or a 0, the target is not found. Other possibility, t is not in 1 to I minus 1 and a at I is equal to t. So 1 to I minus 1 subarray t is not found. It is found in I. Therefore, it is actually in the array. We are returning I. So the algorithm is true. Some thoughts. Generally, you will write the algorithm as shown here. I will not explain that. With a for loop and then say, as soon as the target is found, break out of the loop and return. But I have not returned. I don't prefer this algorithm. The reason, it is difficult to reason. It is difficult to argue about, to reason about the correctness of this algorithm. This is easier. Okay. Another question for thought. Whenever there are two conditions for termination, you should worry about the order in which the two conditions are tested. Should I first test I is equal to n plus 1? Or should I first test a at I is equal to t? Or the order does not matter? Can I take a break here and ask you a question? Does the order matter or does not matter?
Does not matter, sir.
Does not matter. Any other answer? I want at least 3 answers. The order matters or does not matter? One answer does not matter. 2 more answers.
So it does matter.
It does matter?
Yes, sir, it does matter.
Okay. One more answer. Oh, now there is equal voting.
Depends on input.
Depends on the input. What's the name? You are very clever.
Sri Vishnu, sir.
Okay. I want to share a joke with you. I am in a hurry, but I still want to share this joke with you.
Sure, sir.
Sometimes there was a war between Mexico and America. And one man who was living in the border, he wanted to take a neutral stand. So he wore the American uniform pant and Mexican uniform shirt, thinking that, he has taken a neutral position. You can imagine what happened. Americans saw the shirt and shot. And Mexican saw the pant and shot. So sometimes taking this neutral position is not right.
Sir, you expected 3 answers, right?
Yeah, I want 4. No. I didn't say I want 3 different answers.
Oh, okay, sir.
You don't need to make me happy by giving some cooked up answers. Speak your heart.
No, sir.
No means what? The order does not matter. What is the meaning of the word no? The order does not matter. Order of the two tests, I is equal to n plus 1, a at I is equal to t.
Or it does not matter, sir.
Okay. One more person, a fourth person, can you say, when you have two tests, two conditions to be tested for a loop termination, as given here, in this specific example, do we need to concern? Are we concerned about the order? Order matters or not? One more person.
So the order matters.
What is your name, sir?
Survey, sir.
Okay. Linear search is such a famous algorithm. Anyone who is worth the salt of being called a programmer would have been introduced to program with some simple programs like linear search. But linear search is, the body has just one statement, I becomes I plus 1. There is nothing more to do in the body. And it is beautiful because there are two conditions to be tested. If you invert or exchange the conditions, the algorithm will not work. You first test I is equal to n plus 1. Then when you come to test here, that means I is not equal to n plus 1. If I is equal to n plus 1, the algorithm would have terminated. If I is not equal to n plus 1, then you can test A at I. Suppose you interchange or I is equal to n plus 1. And here, I is actually equal to n plus 1. How will the test go? A at n plus 1 is equal to t. However, A at n plus 1 does not exist. You are testing an element which does not exist. Therefore, this will become a runtime error. What do you call exception? This is wrong. The program will not, whenever the target item is not found in the array, this program will throw a runtime error. Therefore, order matters. I can even give a law. Whenever the loop termination condition is a compound condition and there are two or more subconditions to test, it is very important to arrange, to order the subconditions properly. Okay. Anyway, this is not the main point of this algorithm. We are analyzing how many times the loop is iterated. Suppose the target item is not found at all. Is A at I is equal to t? Is A at I is equal to t? This comparison is done. The loop is iterated n times. If C3 is the cost of the basic instruction, I becomes I plus 1, the total cost is C3 times n. The assignment at line 3 is executed n times, and therefore C3 times n. How many times the loop condition is tested or evaluated? N plus 1 times. The last time it becomes true. I am using until. Some of you would be, most of you would be using while. While and until are just complement of each other. Instead of writing until I is equal to n plus 1 or A at I is equal to t, you could have written while I is not equal to n plus 1 and A at I is not equal to t. That's fine. That's up to you. So that is executed n plus 1 times. The cost is C2 times n plus 1. Line number 1 is an assignment. The cost is C1. And therefore, the total time taken is C1 plus C2 times n plus 1 plus C3 times n. But that is the worst case. I have gathered the coefficients of n and the constants. It is an plus b, and therefore finally I will say this is equal to big O of n. What is the best case? Suppose in the input target is found at index 1. How many times the loop body will be executed? It will not be executed at all. Yeah, the loop body will not be executed at all because the first time, A at 1 is equal to 2, t is true. And therefore, here, t of n is equal to C1 plus C2. C1 for line number 1 and C2 is line number 2, and therefore this is constant. So we may say the worst case of linear search is this. Linear, the running time is big O of n. The best case, the running time is constant. How about the average case? For average case, let me say 1 to n is a given array. In n plus 1, I put the target. If the target is in the given array 1 to n, I will be in the range 1 to n. If the target is not in the given array 1 to n, the algorithm will always find the target in index n plus 1. Okay? And the target is likely to be in any one of these n plus 1 positions, n plus 1 indices. It may be in 1, or it may be in 2, it may be in 3, and so on. It may be in n, it may be in n plus 1. What is the probability? Let's say it is just 1 by n, or 1 by n plus 1, whatever. So probability that the target is in index 1 is equal to 1 by n, or 1 by n plus 1. Probability that it is in index 2 is 1 by n plus 1, and so on. Probability that it is in P of n is 1 by n plus 1. The probability that it is not in the array at all is 1 n plus 1, 1 by n plus 1. Okay. If it is in index 1, the loop body will be executed, repeated, iterated 0 times. If it is in index 2, the loop body will be iterated 1 time, and so on. If it is in n plus 1, the loop body will be iterated n times. Therefore, 1 by n plus 1, this, 1 by n plus 1, this. This is sum of I for I is equal to 1 to n. N plus 1, cancel out n plus 1, and therefore this is n by 2. If you discard the constant coefficient, this is also big O of n. So here is the summary. You could have also argued another way. In the worst case, it is the loop body is iterated n times. In an average, it is n by 2. Similarly, the condition on an average will be n by n plus 1 by 2 plus 1. So worst case, a n plus 1, which is equal to big O of n. Best case, a, which is the same as big O of 1, and average case again a n plus b, which is big O of n. So there is no difference between worst case and average case. Both worst case and average case are linear time. Let's check how much time we are left. 11:40. Okay. Here is another example, insertion sort. Let us implement insertion sort as an iterative algorithm. This is ordered insert. Suppose 1 to j minus 1 is ordered. This is sorted. J may be out of order. We want to bring j to in its right position so that, suppose this is I, 1 to I minus 1 is less than item at I, which is less than I plus 1 to j plus 1. You hope you follow. This is my specification. 1 to j minus 1 is already sorted. J is a new element. We don't know whether it may be out of order. We have to find the right position of j. Let me call this the key. In the subarray, let I be the correct position of the jth item. Then we should shift I plus 1 to j minus 1 to the right. All right. That is ordered insert. If I go into reasoning about the algorithm, it may take some time. Therefore, I just present the algorithm. This is the loop invariant. I to j is shifted. Look at that. This is also a compound condition. I is equal to 1 is another condition. or A at I minus 1, another condition. Suppose one to I minus 1. Suppose I to j has already been shifted right by one position to I plus 1 to j plus 1. We are interested, so I is already vacated. We want to know whether I minus 1th item is less than the key. If I minus 1th item is less than the key, right, we have found the correct position for the key. Otherwise, we will shift I minus 1th item to ith position as shown here and decrement the index I. So that I to j has been shifted to I plus 1 to j plus 1 is always true. It is a loop invariant. Suppose I is equal to 1. That is 1 to j has been shifted to 2 to j plus 1. Now you should not test whether item I minus 1 is less than the key, because there is no item I minus 1. Since I is equal to 1, I minus 1 will be 1 minus 1, which is equal to 0. There is no 0th item here. I am assuming all my arrays are 1 to n. Again, this is important. This is a compound conditions. There are two subconditions. The order of the two subconditions matters. First, you should test whether I is equal to 1. Only then you should test, okay, when it comes here, I is greater than 1. Only if I is greater than 1, you can speak about item at I minus 1. If I is equal to, before testing, before ensuring I is greater than 1, you should not do item at I minus 1. All right, let's come to the question. How many, this is a constant operation. This basic operation. Therefore, instead of now writing a C1 or C2 or C3, let me just write 1 for constant. How many times the loop will be iterated? In the worst case, it will be iterated from I is equal to 1 to I is equal to j. All right. So how many times the loop body is iterated? Sum of 1 for I is equal to 1 to j. J times the loop body will be executed. This is insertion sort. Algorithm insertion sort. A comma n, input is an array 1 to n of size n, output array 1 to n is sorted. I have just copied and pasted this is order insert. It works as follows, the basic idea. 1 to 1 is already sorted. 2 is out of order. Call ordered insert on 1 to 2. Then 1 to 2 will become ordered. Call ordered insert on 1 to 3. Then 1 to 3 will become ordered. And so on. Finally, call, actually this is not needed. Call ordered insert on 1 to n. All right. So for j becomes 2 to n. 1 to j minus 1 is already sorted. 1 to 1 is sorted, 1 to 2 is sorted, 1 to 3 is sorted. And after that, we are just calling, this is the code for ordered insert. Oh, including this is also. Anyway, my intention is not to reason about the correctness of the algorithm, but to analyze the running time. There are two loops now. Line number 1 is the outer loop. Line number 3 is the inner loop. The inner loop is the same as before. This is iterated in the worst case j times sum of 1 for I is equal to 1 to j, which is equal to j. How many times the outer loop is executed? Outer loop is executed for j is equal to 2 to n. each time the outer loop is executed once, the inner loop is executed j times. And therefore, the total number of times, suppose I consider this as the basic operation. Basic instruction. Always you select the loop body of the innermost loop as the basic instruction. Loop body of the innermost loop. That is where most of the stuff goes. I mean, whenever you are calculating, concerned about economy, you should look where, however small an amount may be, a small amount which is spent a large number of times will decide the soundness of the economy. If you are familiar with Tirukural, I would quote this Tirukural. Pilibai sagadum achirum appandam sala miguttu payin. Has anyone heard of this couplet?
Yes, sir.
What does it mean? Interesting.
Sir, even though the peacock feather is so weightless, and if we overload a bull cart on it, overload bull cart with more of peacock feathers,
okay. Its axis will be broken.
Yes, sir. The axe will be broken.
What's your name? You are translating well. What's your name?
Nitin, sir.
Hello, Nitin. You are good. Okay. So the peacock feather is the line numbers 4 and 5. The moment you put it inside a nested loop, that is executed, repeated a large number of times. If there is another, maybe it is nested 3 times, an outermost loop, an outer loop, and an inner loop, you should always look at the body of the innermost loop. Okay. Worst case running time. When does it happen? When the input array is reverse sorted. Suppose we want to sort it in this way, but actually the input is given sorted in descending order. This is I minus 1, or maybe j minus 1, and this is j. Every time I use ordered insert, this jth item has to go to the first slot. Because all the items in 1 to j minus 1 are larger than j. Now I want to make it ascending. Therefore, every time, 1 is sorted. Now 2 should be brought to index 1. Now 1, 2 is sorted. 3 should be brought to index 1. 1, 2, 3 is sorted. 4 should be brought to index 1 and so on. 1 to j minus 1 is sorted. J should be brought to index 1. 1 to n minus 1 is sorted. N should be brought to index 1. So that is where the worst case happens. Key to be inserted in the sorted array 1 to j minus 1 is less than all the items in the sorted subarray. Therefore, key will have to be inserted as a first item in the subarray 1 to j minus 1. Inner loop is iterated j times. Outer loop is iterated n minus 1 times. Totally, the inner loop condition is tested. Sum of j for j is equal to 2 to n times. If we calculate sum of j for j is equal to 2 to n, 2 plus 3 plus and so on n, add 1 and subtract 1. This is 1 to, then it becomes 1 to n minus 1 times n by 2. This is n squared by 2 minus n by 2. Discard the lower order term and the constant coefficient. Here I have to be very careful. If it is plus, I can definitely discard. If it is minus, can I discard? Discussion on it later. And therefore, the running time, the worst case running time of insertion sort is big O of n squared. What is the best case running time? Why worst case running time? Okay, here is a very important point. Whenever we are given an algorithm, it is typical for us to analyze the worst case running time of the algorithm. We are not interested in the best case or in average case. What is the reason? Worst case running time is the longest running time on any input of size n. It provides a guarantee on the upper bound of the running algorithm. Life will not get worse than this. I want a guarantee. And I want to prepare myself. So worst case gives such a guarantee. Best case is not a guarantee. And worst case occurs often. And very importantly, it is mathematically more tractable than average case. And it is again an observation. The average case is as bad as worst case. So you may think, oh, we should not analyze for the best case or worst case. I mean, we should not hope for best case, but why should we analyze for worst case? Is not average case a better option? The answer is no. Average case is as bad as worst case. What is the best case running time? Best case is, it is already sorted. Sorted array. All the items in the subarray 1 to j minus 1 are already less than or equal to item at j. Then j is already in the right position. The inner loop will be executed, the loop condition will be tested only one time. The loop body will not even be executed. How about if you consider the outer loop, how many times this basic instruction will be executed? Sum of 1, this is the inner loop cost. For j is equal to 2 to n. Key is already in its right position, hence the inner loop terminates immediately after testing the condition once. Totally, the inner loop condition is iterated for sum of 1 for j is equal to 2 to n, which is n minus 1. All right. So that's the analysis of insertion sort. It's almost time. Worst case, an squared plus bn plus c. The asymptotic running time is big O of n squared. It is quadratic. Best case, an plus b, big O of n, it is linear. Average case, we did not do homework, is also big O of n squared. Order of growth. In order to calculate the order of growth of the function an squared plus bn plus c, ignore the lower order terms bn plus c. Ignore multiplicative constants such as a of the highest order term an squared. And then write this is equal to big O of n squared. This is not exactly right. We will say actually this. The running time t of n of the algorithm is big O of n squared. For small inputs, this running time will have errors. For large inputs, this running time is valid. This big O of n squared is valid for very large inputs for both efficiency and comparison purposes. So we have made the abstractions. Statements have constant cost, Ci, cost ABC, that in turn depend on other constants Ci. Order of growth is approximated by ignoring lower order terms such as Bn, C, ignoring multiplicative constants. All right. Some exercises. Calculate the number of basic steps executed in each of the following algorithms. How many times the loop body is executed? Just one loop. Second example, exercise. How many times the state and min becomes I is executed? How many times the loop body is executed? There are two loops. How many times the for loop is executed? How many times the loop body is executed? Okay, these are very common examples. Okay. Oh, this is the matrix multiplication. There are 3 nested loops. How many times the innermost loop is iterated? These are typical questions asked in CA test. Okay. I stop here.